second speaker is Michael Lentmaier from Lund University in Sweden. Looking forward to the talk on quantitative group testing.
Yeah, thank you for the introduction. I'm very happy to be here, and I'm not just thanking the organizers with the repetition code here, but I'm actually very glad that I can present that work here when Krishna is here, and also Henry, because I'm building on some work that they have done before. So yeah, as the title says, I'm using spatial coupling and low-density parity-check codes for quantitative group testing. So this is a joint work with my PhD student, Mgeni Makambi Mashauri, and also together with Alex Grael E. Amat from Chalmers University. So we're all in Sweden. So what is group testing? We have a large population of items, n in this case, and we're assuming that some of them are defective in some way. You can think of disease screening, but you can also think of multiple random access schemes where you want to identify where users are active and things like that. So you want to identify the positions or those items that are defective, and we use this variable x for it and say it's 0 or 1. And in order to identify them, the trivial way would be to go through all samples and test whether they are defective, but this is complex. So the idea of group testing is to reduce these number of tests that are required by pooling those samples, by pooling those items together and do tests in these groups, like here. So you could take blood samples and mix them, and then you would identify whether one of those samples was defective, basically. And what we want to do is we want to reduce the number of required tests, m here, and we use the rate to somehow say how good this scheme is. If the rate is small, it means we have a small number of tests relative to the total number of items. And then there are adaptive methods that do these tests sequentially and design the next items to test in a sequential adaptive order, but we are here considering the non-adaptive case. So we define the tests, how they are distributed in advance. We don't do this on the fly. And we consider this asymptotic case when the number of items goes to infinity. So we use actually density evolution analysis to characterize it. Or it's a probabilistic recovery and not the deterministic one that we are interested in. So in principle, we can write these tests. We can use a matrix to define which items are included in which of the tests. So every row in that matrix is a test. These are now only 6 items, and we see which items are tested in which test. And this is where we see the connection to codes on graphs in some way, because we could just say every row of this, every test is an equation that corresponds to a check node in a bipartite graph. And these are just the items that are our variable nodes, and then we have check node degrees, variable node degrees. In this case, this is a 2-4 matrix, basically, like we know from LDPC codes. The thing is that what we are transmitting here is not a noisy variant of the items. What we are transmitting, well, we are not really transmitting. The thing that we are observing is actually the syndrome, as in the talk before also. We are observing the test results, so we are calling this a syndrome. So it's the problem is identifying the original vector x from the observed syndromes. So again, we can distinguish between non-quantitative or quantitative group testing. The original results, which are non-quantitative, they basically have at the check nodes an OR operation. So every test tells you whether there is a single or more items that are defective. In this case, all the defective items are outside the test set, but here the other ones all indicate some defective item. But if we go to the quantitative case, then we actually can get the number of defective items from our test results. So this gives us a bit more side information, and this is what we are going to consider here. In this case, we can say that syndrome is basically a normal matrix multiplication with our X vector. But before showing what we are doing, I want to say a little bit what has been done before. There is this work that is called Saffron, a Saffron scheme. That was a work where they used sparse graph codes for group testing, but this was the non-quantitative scheme case. And this is a work that actually originated here at Berkeley, so it's also nice to present it here. And they showed that you can use message parsing and some kind of peeling decoder analysis and do density evolution analysis for actually optimizing and identifying the performance here. And then there is this work by where Krishna is a co-author here, where they picked this up and made a connection to LDPC codes, because the structure of this original work was a sparse graph, but it didn't have this normal kind of scale density feature that we have of LDPC codes. So the idea was to use a Saffron scheme on a lower size as kind of subcodes in a bigger LDPC code. It's a generalized LDPC code where locally we have this signature matrix that comes from the original Saffron scheme, but we can use a base matrix to create a sparse graph where this signature matrix is at these non-zero elements here. And then we are blowing it up and get a bigger, sparser graph out of smaller such subcodes. And they could get some gains by doing it this way. And this was basically a connection to regular LDPC codes, but with this generalized, with the stronger subcodes here. And this was our starting point, and we want to actually somehow do now a slight variation that is interesting for quantitative group testing. In this case, also another set of co-authors with Krishna together have found out that you can actually use a real generalized LDPC code, but this is no longer related to that Saffron structure. It is using BCH codes, T-error correcting codes as component codes, and it was possible for this quantitative scheme to use the error correction radius to peel off parts of this graph in this iterative manner. So it relies on the T-error correction probability. Yes, what actually it turns out is that we can compute the number of tests per subcode that is used here. This is one of these BCH subcodes. It's a Hamming code, actually, with this additional row. And the number of tests is proportional to the number of local errors that you can correct. This is actually a cost that we have here. And the rate can then also be given explicitly for this construction. And the important ingredients of this is that there is
we have the results of Lindstrom from many years ago. Are you going to comment on them? Because the matrix is given to you, you know, it's asymptotically optimal in terms of what you can do, and the algorithm comes directly from the nested structure of the construction of Lindstrom.
This is a good remark. I can't say much about this result, actually, but it would be interesting to discuss it with you later. But what is interesting about, or specific of all these schemes, is that we use this message passing algorithm to do the decoding. And it's all hard decision based on erasures, and we have resolved and unresolved algorithms, items, and we have test to item, item to test probabilities that we can compute based on this decoding radius of the subcodes here.
So I think it allows for probability of error, so that might be the difference.
Sorry?
It allows for probability of error here.
Okay, so
Yeah, we
you're,
have a probabilistic, right? So this is not perfect recovery in that sense, but yeah, so interesting. Maybe I want to discuss with you later because how much time do I have? When I don't remember when I started actually, but
Maybe 15.
I should go quicker, I think. So this is actually the result of that. We have reproduced it. That was our starting point of what has been done in that paper with the BCH codes. And what we're seeing here is the number of tests that we require depending on the number of defective items that we have. And we see that if we have 65,000 samples, we need to do tests in the order of 1,000 or 2,000, depending on how many defective items we have. So this is quite some reduction here. But there's something that is strange in this scheme, and this was motivating our work, is that if we make this subcode stronger, if we increase T, the local code should get stronger, but the performance is actually getting worse. And that was our thinking, okay, there must be something to do with spatial coupling here, because that should have to be to do with this suboptimality of the local codes in that concatenation. So that's the motivation to apply spatial coupling and see how far we can go. Because what's actually happening is also a second thing, is that if we increase the decoding radius, we get penalized by the increasing number of tests that we need. So it's a high cost. And because of that, we were thinking that, okay, what happens if we drop the error correction at all? Can we do something? I mean, going from generalized LDPC to LDPC codes, that was the main observation we made, that actually we just say, okay, T equal to 0 is maybe not so bad. We use single parity-check codes, but then how does the decoder work and what can we do about it? So that's kind of the main contribution, except for the coupling. And then this is an observation actually that my student made. He came up with this on his own, surprisingly, that, if you just look at this, because it's quantitative, you can actually identify two cases. One is that when the syndrome is equal to 0, you know that all of the connected items are also non-defective. And the other is that if the syndrome equals to the test degree, you know that all of them must be defective. So these are only these two cases. It turns out they're enough to peel things off and get better performance than the previously existing schemes. So this is demonstrating how it works. We have erasures in the beginning for everything. The red ones are the defective items. We have these tests. Here we see the syndrome is equal to the degree of the check load. So we know that all these items here are red. We can peel them off from the graph. And then we look at the resulting graph. We see now here is a 0 syndrome. So this must be a defective item as well. We peel off, and now we can identify here equal. So we can go on and identify all of those in a row. So this is how that works. And we can apply density evolution also for this scheme and analyze it and compute thresholds and see how they compare. The only thing that is a bit different to normal analysis of LDPC codes is we have to distinguish now between messages sent to the white or to the red nodes here. So depending whether it is a defective or non-defective items, we get different probabilities here. That makes it a bit more tricky, but it works. And then we get basically for every type, we have two types of equations because we condition on that variable node that we are connected to.
Are you assuming there's noise, or these measurements?
This is noise-free in this case. So what we do now is a performance comparison, and we actually consider two scenarios of comparing. The first one is that we're fixing the gamma. This is the fraction of defective items, and change the rate of the scheme. Basically, we're adding redundancy until we know that it will perfectly, that it will converge, right? So we identify the threshold in terms of we're not changing the number of defective items, we're changing the code rate and see how many tests we need. This is a bit specific, but this is because this was also considered in this prior work here that we are comparing to. And this is actually quite a complicated thing because every time we change the rate, we change the code. We don't have a fixed code. We have a threshold over changing the codes. It's more like a throughput analysis in some way. But because, this is the result that we get here. If we use the original, is the red result. This is a generalized LDPC code. And this is our LDPC code. We have to use a little bit a larger variable node degree, but this is still more efficient than using this generalized LDPC. So we can actually reduce the number of tests in that scenario. But there's the other case is that we try to make it more similar to channel coding and say, okay, we want to make the channel worse when we compute thresholds, not change the rate of the code. We want to fix the rate and then look at what is the threshold for that. And then we're expecting sort of that it's more similar to an analysis and of spatially coupled LDPC codes. So this is that second scenario. So we are, as you see, we're just increasing this number of red items here and see how far we can go. And this is now analyzed here. This is a table of results. This is a generalized LDPC code that was the original scheme. This is the LDPC code scheme, and we see that our result is, again, better than all of those, independently what parameters we choose for the generalized LDPC codes. We don't get as good as this one. This is shown here. These are more like error rate curves now. It's a misdetection rate as a function of how many items are defective. And you can see that the original code is here, and this is a finite length simulation now. And the vertical lines are the thresholds that we can compare to.
Is it spatially coupled? Is one of these spatially coupled?
Not yet, no. And this is for a fixed rate now. We can do it for different rates. So we have these two types of comparisons we can do. If we increase the variable node degree a lot, we see that it gets worse. And this is because we don't use coupling, right? So this is just using regular codes. It doesn't mean that we get better if we make the subcode strong. So the coupling comes now. Can we get consistently better with increasing variable node degree? Yeah, if we use spatial coupling. So I think many here, most of you are familiar with spatial coupling to some extent. The idea is instead of having independent blocks, where we do now in this case is group testing, we are interconnecting blocks. Like in a convolutional code, we have memory. This gives us a spatially coupled system. And what that helps is that, well, we see it later. We can analyze it using density evolution. We have now just spreading it over separate blocks. It's the same type of equations. It's easy to extend. And then our rate is a little bit penalized here also. We don't get a rate loss because in our case, a small rate is good. We get actually a higher rate. But this increase vanishes if we have a very long coupled chain. And then here you see why we want to couple. At the ends, we get basically better protection by having shorter check equations from the coupling. And then if we iterate, this gives this wave-like improvement that after iterations, we can recover all portions of that graph. This is the idea of spatial coupling. And the good thing is that if we use this, we get this kind of universality property that we don't have to cleverly design our degree profile of the graph for different rates that we want to construct. We can just use regular codes and do everything with them. So here, it's not a very dramatic gain for this example here with coupling. The solid line is the coupling. But if we use, for instance, another figure here where we look at misdetection rates versus the number of tests for defective items, we see that coupling even removes some error flow here. This is another side effect that we're getting actually. But if we now look at the LDPC code case, we see that already the LDPC code without coupling is better than the coupled generalized LDPC code here, but we get an additional gain with coupling here. So it was a bit unexpected when we started doing this. We just wanted to couple this scheme, and then we came up with that LDPC variant of it. So now we can look at it more in the perspective of threshold saturation. Here I'm again fixing the rate and looking at what happens if I, what is the gamma that I can, what is my threshold in terms of gamma? And here, this is the reference scheme, and this is an LDPC code. And yeah, we see that we can tolerate a larger number of defective items here. But also we see that now when we use higher degree, this is now the 10 degree, the uncoupled gets worse, but the coupled gets better as expected. This is the threshold saturation effect. So the final question is, can we analyze spatial coupling? Can we prove that this saturates? So up to now, what I showed was basically results that we presented last year at ISIT, but what I show now, this proof of threshold saturation, is a new submission to this year's ISIT, where we actually prove that threshold saturation occurs. So the idea is here to find a density evolution recursion that satisfies the conditions for vector admissible systems. So this is now relating to Henry's work. We use that work of Henry to basically show that we can find such a recursion for which we can prove that we get threshold saturation. In order to do that, we have to modify those equations a little bit by substituting variables and get it into this form, which is actually also looking nicer. I mean, originally this year was a probability to resolving tests. We want actually to have unresolved probabilities. This is the first substitution that we get here. And the other one is moving our gamma variable from that to that part, so that everything behaves like we want to have it in that recursion. And then we can do the same thing with coupling. Those equations with coupling, it's not so hard to do. And now we want to check, okay, can we fulfill these conditions here of a vector admissible system? We need a vector system because we have these two cases, the conditioning on the variable nodes that we had. Actually, we first tried to even find scalar recursions by alternating and things like that, but then we figured out that it doesn't correspond to the original matrices that we're having. So we played quite a bit with it to get there. If we put our epsilon here into a gamma, then we get these recursions from our density evolutions from the previous page. But there's a problem here, because here there's 1 minus gamma and here's gamma. So they cannot both increase. So they don't satisfy these conditions that we need here. So it didn't work, and we tried to do other things and played around. And then finally we came to the conclusion, okay, let's do it this other way. You know, the two perspectives we had. I like this one more, but now I have to admit that the other one is also very important, because if we just, this is the same as before, if we just set epsilon equal to 1 minus 1 divided by the degree, we basically get to this scenario where we fix gamma and then change the rate instead. And in this case, we can basically have this epsilon. It's not a continuous variable. We have to change the degrees to basically change rates. We cannot sweep it continuously, but we can map it to a function that can apply here, and that's a trick that can be used to make it work, finally. And then we can prove that threshold saturation occurs. And then we can define the potential function, and it worked out to even explicitly derive it for this case. This is a plot for this potential function. We have these two coordinates, and this depends on kind of the value of epsilon we have. And in this case, everything is non-negative. So we actually look for the parameter epsilon for which this function is touching the all zero plane down here, and that gives us a potential threshold. And if we do so, then we can get this graph here. Now, this is our fraction of defective items. This is the rate, and then we get these curves for the potential threshold. We see they get better and better. They get smaller if we increase variable node degree, but they tend to converge to something. And now it becomes interesting, because I would like to discuss with you guys what do we guess what that limit is? Maybe it's the limit that Olgica mentioned. I don't know. Because if we use LDPC codes for communications, we know that increasing the degrees will bring us to capacity. But here we don't know what the capacity is. Is there a capacity? So the question is, what does it really converge to if we make our coupled code bigger, stronger and stronger and stronger? So that's an interesting open question, I think. And also to just verify that if we take our rate equal to 5 as I did before, and go here, this 1.3 is exactly the threshold that we have earlier saturated to numerically. So it actually coincides. And so we don't need a separate view of these thresholds. It's both in that figure. We can either fix omega and look for the gamma, or we can fix the gamma and look for the omega. It's enough that we can compute it in one way. Okay, that's basically it. We have shown that using simple LDPC codes actually can outperform these pre-existing generalized LDPC code constructions based on PCH codes. And we have also shown that we can improve with coupling for both schemes, get an improvement, and we can combine it to get the best of everything. These two views of what we change for computing thresholds we have seen, and we have proved saturation to the potential threshold. And what we are currently working on is looking at some variations where we use non-binary messages to improve this further. And we do this by bundling text together in groups so that we have a higher alphabet in the message parsing. And in the future, maybe we look at more soft decoding here. Okay, thank you.
Maybe a couple of questions.
So if you take a measurement, right? I mean, one guess would be that you just simply look what's the maximum entropy you can get out of a single measurement, right? So, depending if you make it higher, you get different distributions. Whatever the thing is, you will have an entropy into it. You maximize that, and that should, that would be, I guess, what it should be, right? If you say independent.
Guess of the limit, you mean, or?
Because you know how much entropy there is in the sequence that they have to resolve, right? Because that's just that's just the Bernoulli sequence, with a certain parameter.
And that gives a bound, right?
Huh?
That gives a bound.
Well, it gives you can certainly not beat that, but if you get that, then you would know what it is.
That's not clear that you can get that, I think.
Well, as you're increasing the degree, I think in this model, the entropy just keeps going up, right? Because it's just the sum of some number of Bernoulli random variables.
Yeah, but we'll also concentrate, the distribution will concentrate, right? So it's not clear.
Yeah.
But it's an interesting. And then comparing to the bounds that you mentioned.
Those are any number of defectives. We can go to an arbitrarily high number of defectives. And it's a very special matrix structure. And as Hassan said, it's zero error. My question was, if you have something like that, in what case do we decide to go with that scheme, Lindstrom scheme versus?
That's a good question. What about the decoding algorithm?
Oh, Lindstrom's matrix is beautiful.
So the complexity?
I don't think so. I don't think it's so complex. I mean, my opinion is the decoding approach is very straightforward.
And I just want to add to this. In some way, we started using this scheme because it were generalized LDPC codes. But I also talked to Makambi that, okay, what happens if we do this with non-quantitative? Can we do anything? And first thought is you can't do anything because you don't have this extra information. But actually, he tried it out and he said that he can beat the original schemes that I have shown here also, even in that case, with a simple LDPC peeling decoder for the non-quantitative cables.
That's one more question. There is a world between binary outcomes and quantitative outcomes, semi-quantitative, which is more practical. I was really interested in how would the equations look like in At least to me,
Yeah, and
see if you can prove something for spatial coupling, because you really never get the right count. I mean, if you have the outcome of a real experiment, you're going to tell roughly it's in some interval. If the output is not really 2 or 3 effectives.
but I don't really think that there are lots of possibilities to deepen that. It was a starting point because that was very, very easy to do here. I mean, the first intention we had was also to looking at, for these generalized LDPC codes, we said maybe we can do better than just decoding error radius. If you use a better decoder than bounded medium distance, maybe you can also improve things. And then thinking about different ways of soft information was the next thing to think about. I think a big question is, I mean, running it is not the problem with soft decoding, and this has been done. I mean, BP decoding of group testing schemes, but analyzing it, I think, is a bit more complicated. So that's why we started with that.
Luigi had a question and then you will.
It's along this line. So you didn't try to run BP for a finite length simulation here, because you have of course information also when you find, for instance, that the number of defective elements in a test is 1, right? You can compute then a probability that you can send down to the variable nodes.
Yeah, I think you can get better if you use soft information in BP.
But you didn't try to simulate
Not beyond those things which we did with your examples.
because that will already, if you improve over the simplified decoding that you're using, then this is already a sign that probably saturation is not happening towards a limit, because we know that there is something that is going to work better than that. So you have your saturation effect, but it's under a suboptimal message passing algorithm.
Well, it depends. You can think of it as also a different channel in some way.
Yeah, or a different.
Because we don't have priors here.
Maybe it's also a question to Krishna. What's the original reason to use GLDPC and not start with the more natural LDPC?
That's a good point, yeah.
I don't know. I mean, I have to. With the GLDPC, we were able to exactly figure out if there were 1 or 2, which items we could pinpoint which items were defective. We had less than T defective items, so the T thing was pretty obvious. I'd have to see exactly what happens in the LDPC, because in the LDPC course, then we cannot really peel things off. We won't identify exactly which items are defective in one measurement, right? So I think the analysis is probably more complicated in the LDPC code case.
A little bit, but because it's a very simple code, it also was okay to do it. But I think the elegance about that T error correcting code is that you don't even have to be able to decode it, and still you can analyze it.
Yeah.
It's
Let me mention that I think in the problem with quantitative group testing is much closer to compressed sensing. And I think in the compressed sensing case, the rule you mentioned of seeing the zeros in POD is actually analyzed but it's also used for like large alphabet LDPC by Google and Lentmaier for a long time ago. And then we used it extended it for compressed sensing. So so you might also compare some literature in compressed sensing.
Yeah.
So what's your
Testing and compressive sensing are really intertwined.
But if it's not quantitative, they're somewhat different. But if it's
No,
quantitative, they're very close.
But they're related, especially because of COVID, I guess. Group testing approaches.
I just because you mentioned it, I tried to get funding for this in Sweden, but maybe you have heard of it, that there's no COVID testing in Sweden. So it was just an attempt that was useless. No application there. We don't want to test group. You don't want to, so we can't give you money.
Influenza.
All right, let's thank Michael. Okay.
Thank you.
Before we take a break, we have a lightning talk session